Alright guys, the next chapter is about using arrays, sorting them, and searching them. We've already talked about how to search an array. You just start at one position of it and go through to the end of it. And writing a sort algorithm, I'm just going to kind of skip that. If you want to read about it, it's a good idea. Sort algorithms are interesting, but I don't think they're mandatory, because in the real world, if you were going to use a sort algorithm, you would use one that already exists rather than come up with your own. I want to talk about namespaces just for a brief moment. Using namespace, std. Why do we do that? You know why we do that, so that we don't have to put std : in front of our cout statements. We can make our own namespaces, right? Namespace, Lecture U. Why in the world would I do that? Well, I can put functions in here that might have similar names to other functions that are in our code base, right? You might be working in a large project with a whole bunch of different files in it, and there may be a whole bunch of different functions that have things like open or open file, right? So if we need to write an open file, I'm just gonna dummy it up, right? It takes a string, that's a file name, right? So we better # include string as well if we're gonna do this, right? And I'm not going to actually open the file. I mean, I guess I could, but nah. We've done files already. Cout, file opened, followed by the file name, followed by India, right? That's all it needs. Now, what if there was an open file in a different lecture? Not a different lecture, a different file in the project. Then how would it know which one to use? Well, since we have put it in a namespace, we can refer to it, right? We can say Lecture U : open file. In the C# language, you're supposed to, whatever, output.txt. In the C# language, all the code you write goes into namespaces. Usually a different namespace per file, so that you can just refer to each one like that. Now, that way, you can write your functions without worrying that your names, your global variables, your function names, your classes don't overlap with ones that other people may have written for the same project, right? Because you could write something else that has an open file in it too, right? Namespace, we're coming up with some test code, right? And it's also got an open file function. This one's going to do even less than the other one, right? It's just going to well, I mean, I guess I could, but anyways, I'm not going to actually run these, but if I wanted to run that one, test code : open file. Just like that. So this, what are you complaining about? Nothing. All right. So, yeah, I'll just put a cout message. This was Lecture U : open file, and this is, right, test code file open, right? And we can refer to which one we need. And if it turns out that we use this one 99% of the time in our own code, in our own file, we could do using namespace Lecture U, right? No colon there. Then whenever we wanted to call open file, it would call that one. Because we no longer have to precede it with the magical word here, Lecture U, to point it to this one up here. That's what namespaces are. They're just a way of divvying up your code. Okay, so we've talked about pointers. I wanted to look at the PowerPoint for pointers. So getting the address of a variable, we have done this. I've shown you that if you use the ampersand in front of a variable name, it gets the address of it. So if I want to do, declare some variables, int x, y, z, and I'm curious about their addresses, I can do ampersand x followed by a space, followed by ampersand y, followed by a space, followed by ampersand z, followed by a space, well, followed by ENDL, right? Now that's not going to print out their contents, which they don't have any, right? X is equal to 1, y is equal to 2, z is equal to 3. It's going to print out instead what byte they are stored in memory, unless there's an error. ENDL. Oh. I forgot my arrow here. There we go, right? Sometimes it helps my brain if I divvy them up like that. Run it. All right, and so here's the addresses of those variables, right? It's interesting that they kind of go down rather than up. X is at the highest memory address. Y is, or A, B, and C, is that what I call them? X, Y, and Z. X is at a higher memory address than Y, which is a higher one than Z. It's just a way that, we have no control over how those are allocated, where they are allocated. And that's a good thing. We wouldn't want to have to specify individual bytes. That's like 1950s style programming. Okay, so, and then what can you do with that? I'm going to declare some pointers to those addresses. This is a pointer to the X variable. This is a pointer. Well, why don't I declare 3 of them at the same time? And a pointer to the Y variable and a pointer to the Z variable. And Px is equal to the address of X, Py is equal to the address of Y, and Pz is equal to the address of Z. Okay, fine. It wants me to put a star in front of each one when I'm declaring them. And it's just a common convention, one you don't have to do, is that if a variable is a pointer, you give it a name, P. All right, so what if I wanted to pass those to a function, right? I'm going to call the function change values. Sorry, guys. All right, so it's going to be called change values, and it takes 3 pointers: int star p pointer 1, int star pointer 2, and int star pointer 3. Now I'm going to print those addresses out just like I did the last time. But separated with commas this time, just to make them look different. And I'm going to divvy them up like I did before because it helps my brain sort out, make sure I didn't miss any. Okay, that looks good. Now, why didn't I put ampersands in front of these? Well, I'll show you. So I'm going to scroll down and call change values and pass those pointers to it, right? Change values, px, py, pz. So it runs, and here's our memory addresses. These are the bytes that those values correspond with. And inside the function, we also have those addresses. And that's why we didn't get the address of these, because we don't want the address of the pointer variables. The pointer variables already have addresses. That'd be like if I gave you a piece of paper that had an address you were supposed to drive to get another piece of paper that had my address, right? It's an address to an address. And that could be useful, but more often than it's not. Anyways, right? So these are actually different values now because they're the addresses of those variables, of the parameter variables, the values that were passed in. So we don't want the addresses of the parameter variables. We want the addresses that they contained. And so let's change those values. Let's double each one. They were 1, 2, and 3. So ampersand P1 times equals 2. Ampersand P2. Okay, let's just add 1 to it or something. Or set it equal to 100 and 200 and 300. That second asterisk was just to be a multiplication, but it kind of made it look like it was pointer notation since it was, you know, preceded by that. So I don't want to do that. And then if I go and print those values out, what I'm going to do, I'm just going to take this, copy it, and paste it, and remove the ampersand so that I can print the values, right? X, Y, and Z will have changed values. Right? And so when we get back from the change values function, we have 100, 200, 300. It's about time for us to get rid of the hello world message, isn't it? Okay, let's go read a little bit more. So that gets the address of another variable, and you can use that address to change the value of the variable. When you're using the address to change the value of the variable, you put an ampersand in front of it. And technically this would work, right? If I wanted to change the value of it to -100, this gets the address, and this is what's known as dereferencing it. I'm not sure that this textbook calls it, but we are dereferencing that address. And so now we have changed the value of num to 100. Now, nobody would ever do that, right? Normally, if you're going to use the asterisk to change the value of a pointer, then it's in another variable, right? And sure, you could do that, right? You could declare a pointer to num and get the address of num, and then you could change it. Star pnum is equal to, you know, -100, and that would change that value. Like that. So pointer variables often just called a pointer, holds an address. Because a pointer variable holds the address of another data, it points to the data. It's like if I give you a piece of paper with my home address in it, you can go to my house and then you can change it. I don't know, paint it red, whatever. So we've already dealt with something that were similar to pointers. We've done arrays. An array is just a memory address. For example, suppose we use this statement to pass the array numbers to the show values function. We have a function called show values, kind of like our print array or whatever we called it. That address, that array value, is actually just an address. So when we did this, when we declared an array of 3 values, right, equals, 7, 8, 9, and then we pass that into a function, void print array, so that we could print those values out. See out, ARR subscript 0 plus ARR subscript 1 plus ARR subscript 2. What are you complaining about? Oh, that's in the wrong place. That's Java syntax. Java puts the braces before the variable name rather than after. Okay. So there. So it's going to print out 7, 8, or 9, or whatever I set those values equal to. It's not going to even put spaces between them, is it? All right. So anyways. Oh, I guess I never actually called it. Put some commas between them. All right, so down here after we've declared our array, we're going to call print array and pass in that array. What are you complaining about? Print array is undefined. What did I call it? Oh, excuse me. I called it print ARR. All right, there we go. Right, and so it printed out our array. Well, it printed out 9. That's interesting. Why did it print out 9 and nothing else? All right, I don't get it yet, actually. Let's define this in a more traditional fashion. Const int ARR size equals 3. Let's use that const int as our size declarator, ARR size. Let's make it so that this function accepts a value, which is the size of the array. Let's scroll up and modify our function to actually accept that value. And then let's make a for loop that counts up to that value, right? For int I equals 0, semicolon, I is less than size, semicolon, I plus plus, cout, array, sub, followed by I, followed by an equal sign, followed by the array value, followed by ENDL, just so we can see all the values. Well, what the heck? 7, 8, 9. How come when I called it? What did I have? Why didn't that work? Why couldn't I just cout ARR subscript 0 followed by ARR subscript 1? That's just effectively what I had. Followed by ARR subscript 2. Followed by ENDL. All right. When I did that, I was just printing 9 rather than 7, 8, 9. Oh, and now it's working. All right, great. Okay, anyways. So, this thing here, ARR, is just a pointer. I could get a hold of that first element by using the asterisk, like I did over here when I was changing values. I could do cout array by pointer less than, and then asterisk ARR. That's the first value in the array because it's the first bytes in the array. And it's also going to be 7. ENDL. Right? That's because this is really just a pointer. It's a pointer to the first element in the array, the bytes of the first element in the array. Well, what if we wanted the second one? You would just say that array plus 1, that pointer plus 1. And what if you wanted the third one? That one by 2. And so this is going to print out 7, 8, and 9 again. Right there, 7, 8, 9. So an array is just a pointer. And you can access each element in the array by dereferencing it with the asterisk and then adding 1 and 2 to indicate which array element you want to get a hold of, right? That would, plus 0 is the first element in the array, plus 1 is the second, plus 2 is the third. This business here of using subscripts, it's just to make it look nicer. We could have been doing this all along. I momentarily changed chapters. Where's my first one? There he is. We've also worked with reference variables, but really they're not reference variables, they are pointers, so I'm going to skip that slide. So pointer variables are another way of using a memory address to work with a piece of data. They are more so-called low level than arrays and reference variables. I would say that they're the same level as arrays. This means you're responsible for finding the address that you want to store in the pointer and correctly using it. So here we have a pointer to an integer. So int pointer can hold the address of an int. I would just say int pointer is a pointer to an int. Spacing doesn't matter. You feel like sticking the asterisk over there, or you want to put it right next to the variable or somewhere in between. I think most people do it like that, but I don't know. Assigning an address to a pointer variable, just like that. Now int pointer has the address of a variable named num. And so int pointer contains that byte number, and the bytes actually contain the value 25. They're kind of missing something, right? Int num equals 25. Should have been like that, maybe on a line above it. Be nice if they were all in Courier. All the same size. Anyway, there we go, right? Good enough, right? That means that when this was created, it was created in byte number 4A00. And so if we get the pointer to this variable, then the pointer to that variable is 4A00. And the 0x in front of it just means it's a hexadecimal number. So you can initialize pointer variables with the special value null pointer. I don't know. I always thought people just didn't initialized it to null. But I learned C++ before 2011, so they made a new keyword. Not sure why that's better. Anyways, when we create our variables, I guess we could be setting them equal to null pointer. Honestly, I don't care if you do that. Most people, when they create them, just set them to null. Null is also 0. Oh, well, that's why. I forgot. Null is actually not defined in the C++ language. It is in C# and in Java and quite a few. Okay, cool. So there's a point to it. Or you could just set them equal to the number 0, but that's a little bit more cryptic. So the indirection operator, I was calling it dereferencing it. They're calling it indirection. You want to change the value of this variable by its pointer, then you use the indirection operator, which is the asterisk. And like I said, it's normally called dereferencing. Why is it called dereferencing? Because int pointer is a reference to the address of x. So if you want to change x, then you dereference it. Now that usage of the term reference is not via the actual reference that we were using when we created our variables in a prior lecture. You remember that? You can also create variables that look like this. You know, string A equals Bob, and then string ampersand B is equal to A. That means B is A. Not that B is a copy of A. B is A. So if we change Bob to Sam and then we print out A, it's going to print out Sam, right? Because A has now been changed to Sam. This is not a copy of A. It actually is A. We just have two names that are the same thing, just like, you know, I have two names. You call me Yo Professor, or you can call me Yo Jeff, and I'm going to do the same thing regardless. There we go, right? Sam. So the relationship between arrays and pointers, I've already talked about that. Pointers and expressions. If we create an array and we create a pointer to an int and we say that that pointer points to that array, then what is val pointer plus 1? It means the address of val pointer plus 1 times the size of an int. It actually does a little bit of math. It does a little bit of math here. It behind the scenes, because if this was an array of doubles, then the size of a double is 8. The size of an int is 4. It's just doing a little calculation here so that we don't have to do plus 4 to get to the next int and plus 8 to get to the next int. It figures it out for us. And we already saw that this syntax, you could actually leave that out and it still figures it out. And I don't know why, what magic it does to do that. But anyways, this is the second element of the array, and that's the third element of the array. It says you must use those as shown in the expressions. Well, I beg to differ. All I did is copy and paste that code. And why don't we print out the 4 as well, right? So I'm going to take out the plus 1, or I can make it plus 0, but anyways, it's going to print out 4. I did unpause it, did I not? Good. All right. Right, so it prints out 7, 8, and 9 because those are the values. No, wait. I was looking for 4, 7, 11. Should have been below. There they are, 4, 7, 11. Would it work without the parentheses? I'm going to crash. What is it doing here? Did this syntax not work here? It's exiting immediately now. What are you doing? All right. No, it's not. All right. I'm wrong. I am so wrong. You actually have to have the parentheses there. And the only reason it worked is because I had my values consecutive, right? When I declared them as being 7, 8, and 9. If I made these variables up here, wherever I declared those 7, 8, and 9s, well, lo and behold, I was wrong. That's all right. I'm always willing to admit when I'm wrong. 70, 80, and 90, right? My code would have printed 70, 71, and 72, right? 70, 71, and 72. So the parentheses are necessary. My mistake, and I apologize enormously for doing that. Here we go. Now to print out 70, 80, and 90. All right. Well, I'm glad I won't mess people up on that again. So if you do that, vals subscript I, that's the same thing as doing star, vals, star, parentheses, vals plus I. And one more little weird oddity. I mean, it's not that weird, and it's not that odd. Just a fact of life. If we set val pointer equal to the array variable, it contains an address, and if you add one to val pointer, it actually bumps it up just like that does. So if we print it out now, so after val pointer plus plus, then we print out cout, wait, star val pointer, just like this, like we were doing here. Val pointer is now pointing towards the next int, right? The plus plus doesn't change the value. It's not going to change that 4 to a 5. It's going to change val pointer so it's pointing to the next int itself, which is a 7. So we're going to see it print 4711, and then we're going to see it print after val pointer plus plus 7. And so it does, right? 4711 and then the 7. And I guess I should put some spaces here, or carriage returns or something, because they didn't, but it makes it easier to read, doesn't it? Pointer arithmetic. If you do plus plus or minus minus, oh, I just said that, right? When you add one to val pointer, it now points to the second element in the array. When you subtract one from it, it now points to the first element of the array. And that's true. If you subtract two pointers from each other, you get the number of elements, I guess. I never thought about that. Val pointer minus val, that's the difference between val pointer and val, the number of ints. Okay, well, we could prove that, I guess. Well, I mean, makes so let's set val pointer back to the original address, and then let's make another one, int star val pointer 2, that's equal to the address of vals, but let's increase it twice, right? Vals plus equals 2. No, val pointer plus equals 2, excuse me. Val pointer plus equals 2. This one points to the first element. This one points to the last element. And so if we subtract them, well, 2 minus 0 is 2, right? I don't even really see why we needed to put a big slide about that, but so the int difference is equal to val pointer 2 minus val pointer. What is it? It's 2. Because it's 2 ints back, right? This points to the first int and this points to the last int. 2 ints back. Onward. Initializing pointers. I think we know how to do that. If you're pointing it to an array, you don't use the ampersand in front of the array variable name. If you're pointing it to a single int, you do use the ampersand. Can't test for an invalid address with not pointer. But what if it was null? Nah, I don't see how you would be able to do that. Pointer math is dangerous. If you access the wrong memory, like if we did something like this, if we said cout less than asterisk parentheses val pointer val ptr plus 10, or what if we increased val pointer by 20 and then we tried to print out the element at val pointer now, right? Val pointer, right? I'm going to delete some of this stuff. Well, it's no longer pointing anywhere in the array, right? It's pointing 20 past that element. And so if we change it, if we change a value via using that pointer, we have now changed data outside our memory range. Whatever, right? The debugger might even throw an exception. And as a matter of fact, it did, right? Because we changed memory that we don't own. This would change memory (80 bytes) past the first element of the array. Why 80 bytes? Because int size is 4. Val pointer has now been increased by 4 times 20. In an effort to point it at the 21st, well, I guess the 20th element of the array. Yeah. So since the array is not that long, we are accessing past the end of the array into memory we shouldn't. And this will probably crash. It'll at least not do anything we want, right? We certainly don't want to be mucking around changing values we shouldn't. Comparing pointers. You can compare your pointers. Comparing addresses and pointers is not the same as comparing the contents, right? This compares the addresses. This compares the values. Well, that makes sense. If you have two variables, right, so what's the first element of our array? It's 4. Let's declare a new variable called 4, like that. And then if, okay, maybe that's silly. I'm going to call this XYZ. And then so if the address of XYZ is equal to val pointer, let's reset val pointer so that it points to the original value of the array. And so if asterisk XYZ is equal to asterisk val pointer, we're checking the contents. And of course, I need my parentheses in my correct places. Why are you complaining now? Oh, because I forgot to make it a pointer. I forgot to put my asterisk there, right? Actually, what oh, my brain. I want to make a pointer to XYZ. Now, int star p XYZ is equal to XYZ address, right? And now, when we compare, if we try to compare XYZ to val pointer, they're not the same at all, right? Because they're not the same address. So we're not going to see that message. We're not going to see same address. But I'm going to copy and paste that. If we check their contents, the values that they point to, if we dereference them, then they will have the same content because we set it equal to 4. It flagged it as an error and then as not. What am I doing wrong? Oh, I'm forgetting my semicolon because I'm trying to be sneaky and put it all in the same line. There. Teach me to use bad formatting. There we go, right? Now we're good to go. It's going to run and say it's the same content, but it's not going to say it's the same address. And we could actually absolutely prove that it's supposed to be the same content by saying that I want the first element of the array, and I can set the first element of the array equal to 4, right? It already was 4, but there we go, right? So they're both should be set to 4. Set the first element of the array to the value 4. Okay. And indeed they do have the same content. Looks like I could have used an ENDL here. Pointers as function parameters, we've already talked about that. So here's a function called swap that takes 2 pointers. And since they are pointers, we can change the value by their memory address. And so if we pass in the address of 2 variables, where num1 is equal to 2 and num2 is equal to 3, by the time we've called the function, the num2 is equal to 2 and num1 is equal to 3. They've swapped the values. Right? So to pass the values in, if it's declared, if the parameter variable is declared as a pointer, then we need to get the address to pass in as our argument. So we're using the ampersand to get the address. If we want to store the address of a constant in a pointer, then we need to store it in a pointer to const. Well, that's not helping. You can make a const double. Let's just declare that. I mean, let's demonstrate that in code. All right, so I have a constant, right? Constant double E is equal to mc squared. C is the speed of light. What is the speed of light in meters per second? Yeah, 3e to the 8. 2.998 e to the 8, right? So 2.998 e to the 8. That's the speed of light. And I guess I could use a whole variable, right? So there we go, right? We have a constant. If I want to make a pointer to it, I need to guarantee that we're not trying to change its value. Const pointer star, I'm going to call it PD, a pointer to a double, right, is equal to the address of speed of light. So if I want to write a function that accepts that, I'm going to write a function. I'm going to write it here and then I'm going to copy and paste it anyways. So void print SOL, and it's going to take a pointer to a double, and we're going to print it out. Cout SOL equals less than star PD ENDL, right? Okay, so I'm going to cut this and go and put it where it needs to be. I could put it below main, but then I would have to declare prototype. So I'm going to come up here and declare it above. All right, so is it going to print SOL? So I'm going to print 2.99 e to the 8. I think I actually forgot to call it, right? So if I do print underscore SOL and I pass the address of the speed of the light in, or I could have just passed in this variable, right? Print sold? No. Print SOL, pass in PD. It's complaining. Argument of type const double is incompatible with parameter of type double. Same business here. This double is a const. So if we're going to get the address to it, we have a pointer to a const. So in our code, we have to say, you're a const. Why does it do that? So we don't try to change it, right? So we don't say PD, the speed of light is now suddenly 10, right? Well, no, it's not. It's a pointer to a constant. We're not allowed to change it. Can't do this because PD is a pointer to a constant. Can't change the constant. If we try to, it's a syntax error. All right, I think that's about enough for this lecture. Dynamic memory allocation is an important topic. Why don't we hold off and do that the next lecture? So what's our homework going to be on this one? It's going to be incredibly easy because it's going to use code that's already in here. No, I think I won't. I think I won't assign code over this, homework over this. We may have one more homework assignment based on next week's first assignment. We'll see. Alrighty. So, hope this was educational, and I will see you next lecture.